Kia ora Year 12 and Year 13. This video is to help you with how to convert complex numbers from rectangular to polar form. And I'm going to go through how to do that and then how to multiply and divide in polar form. I'm using two examples in here for which you're going to need your calculator, so please go grab it. So next video we'll do one where we're using the special triangles, which I know all of you love so much. So this goes with the really old Delta book, chapter 18.1. But the old Delta book that, if you're watching this from another class, you'll have is probably chapter 32.2. So that's the second edition with the pink cover. The two numbers I'm working with here are z is equal to 7 minus 5i and w is equal to negative 4 minus 9i. Now I've picked those because when you look at where they sit on the Argonne diagram, they're not in this nice easy first quadrant here, right? So when things are in the first quadrant, most things get easier, right? So if we've got one that is up here, so suppose we've got 4 plus 2i, then we can put the point on there. And what we're looking for when we turn a number into polar form is to go from this form into z is equal to r cis theta form. Now the cis theta means r times cos theta plus I sine theta. R is the length of that line and theta is the angle here. So when we're working in the first quadrant, it's pretty easy to see how to find that angle and that length. So the magnitude z is just Pythagoras, right? It's the x coordinate and the y coordinate. So it's the 4 and the 2, right? It's not the 2i, it's just the 2. And that stays the same, whatever quadrant we're in. But the angle we're looking for here needs a little bit of adjustment. So in the first quadrant, the angle will just be tan inverse of this length over this length, right? Back to Year 10 trig, the opposite over the hypotenuse. But once we start being in different quadrants, we have to be really careful because the value that our calculator returns is not going to give me the correct number. So let's have a look at what we should be getting for the angle for these two complex numbers. Well, here's for z, you can see that the angle should be, oh, where's my pen gone? Here we are. So the angle we want should be in here, and that should be between 0 and negative 90 degrees, right? Remember, we measure our angles clockwise. And for w, the angle we get here should be between negative 90 and negative 180 degrees. So in general, when we're finding theta, we start off by doing a tan inverse of the y coefficient over the x coefficient, but then we need to make this adjustment. So no adjustment is needed if we're in this quadrant, and none is needed if we're in this quadrant. If we're over here, we take off 180 degrees, sorry, we add on 180 degrees or pi, and down here we subtract pi. And we'll see why that happens in a moment. So let's look at our first one. We've got z is equal to 7 minus 5i. That's in rectangular form. The magnitude of z is the square root of 7 squared, 49, plus the negative 5 squared, which is 25. And that gives me the square root of 49 plus 25, so 74. And that's roughly equal to 8.60 to 3 significant figures. The argument here is equal to tan inverse of negative 5 over 7. And that gives me negative 0.620 in radians, or in degrees, negative 35.5 degrees. I've done this video in degrees because I think most of you are probably better at thinking in degrees still. Hopefully, though, you should look at that and see that that's going to be somewhere in the negative 30 degrees. 1 radian is about 57 degrees. So it's a good basic fact to have in your head. So if you look at what's going on in here, when we put the this into my calculator, the calculator is giving me the right answer for this one, right? We're in this quadrant down here. The number that we got out made complete sense. We got negative 35.5. So z here we can now write as z is equal to 8.60 times cis of negative 35.5 degrees. So that's that first one done. Now when we do the same thing for w, we're going to get a positive value out instead of the angle that we want to have in that range. So for w is equal to negative 4 minus 9i, The magnitude is going to be this. So we've got 16 plus 81. That gives me the square root of 99, which is roughly 9.95. And the argument will equal tan inverse of y on x, and then minus pi. So let's see why that's got to happen. Well, when you put -9 over -4 in here, the calculator is of course going to calculate that as 2.25. So we're down here, but the calculator thinks that we are up here. So the value we get back is this one. We have to adjust it by taking off pi. So you hopefully will get used to that pretty fast. It's one reason why you do need to do plenty of fluency practice on this skill, so that it just happens automatically when you see it in an exam problem or in a real life problem. Okay, so here we get -1.989, and that's about -114.0 degrees. And that looks perfect when we go back to, where's it gone? My diagram here. Right, so that looks pretty good. It's round here more than 90 degrees, but not that much more. So writing that out nicely for the 2, we get Z is equal to 8.60 cis of -35.5 degrees, and W is equal to 9.95 cis of -114.0 degrees. Now to multiply complex numbers in polar form, it's really easy. We multiply the magnitudes and we just add the arguments. So my way to remember that is MMAA. Right, multiply the moduli and add the arguments. So ZW is equal to 8.60 cis of -35.5 times 9.95 cis of -114.0, giving me 85.59 cis -149.5 degrees. Right, so we just add those two together. For division, it's similar, and we didn't do the division proof in class, but it's a lot like the proof we did for multiplication. So this is what I want to do. I divide the moduli and I get 0.865, and then I subtract the arguments. Now that gives me a very short length complex number with an angle, an argument of 78.4 degrees. So there you go. Now go and do some of the exercises in 18.1, and don't forget to update the tracker sheet at the end of it.